Hey everyone, this is Dr. Marie McNeely, welcoming you to episode 806 of People Behind the Science. Today I am joined by our guest, Dr. Jia or Leo Lee. And I want to take a moment to thank you for listening today and to give a special shout out to everyone out there who has been sending us emails and rating and reviewing our show. We love getting to meet you and getting your thoughts on the show. So if you haven't introduced yourself yet, you can send an email to us at contact@peoplebehindthescience.com or get connected with us on social media. And today we have a great episode, so get ready to meet another one of our amazing people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to People Behind the Science. Today, I am excited to be speaking with our guest scientist, Dr. Jia or Leo Lee. So, Leo, welcome to the show today. How are you?
I'm doing great. Thank you very much for having me.
Well, Leo, we are excited to have you with us, and we're looking forward to learning more about you and the work that you do. But before we get into those details, let me take a moment to tell our listeners a little bit more about you and how you got to where you are today. So listeners, Leo is an associate professor of physics at Brown University. He completed his undergraduate studies at Tsinghua University in China. He received his master's degree and PhD degrees in physics from Northwestern University. And afterwards, Leo worked as a postdoctoral researcher in physics at Columbia University before joining the faculty there at Brown University. Now, he has been the recipient of a number of awards and honors, including a Sloan Research Fellowship, a National Science Foundation Career Award, and Brown University's Salamon Faculty Award for Excellence in Scholarly Work. And Leo, today we're excited to get to know you, both as a researcher, of course, but also as a person. So can you tell us, what do you like to do when you're not doing science?
When I'm not wrestling with experimental issues in the lab, usually you can find me in a rock climbing gym or on a running trail. Running is my mental whiteboard. Nothing really clears a stuck equation or frustration from a failed experiment like when you're running on a trail. Plus, there's some kind of parallel between finding a perfect running route compared to finding an elegant solution to a physics problem in the lab. So climbing and running is usually what I do when I'm outside of the lab.
I love it. And I think you're absolutely right. Sometimes stepping away, getting your body moving is a good way to overcome those roadblocks that you hit in science. So we talked about what you like to do outside of science, and you're doing some remarkable work in the lab, Leo. I'd love to chat about that next. So how do you describe your work to someone who is outside of physics or perhaps outside of science altogether?
So you can imagine shrinking a sandwich so thin that it's just a few layers of atoms. That's kind of the material that I study. And what I do with these material is exactly like building a sandwich. It's like how you stack different ingredients to create a new flavor in a sandwich. I stack different layers of 2D material together to discover new electronic properties that could revolutionize future technology. You can also think of it as atomic level Lego building, but instead of making toys, we're creating new materials that could power next generation of computer and electronics.
I love it. I think that's a really accessible way to describe some complex physics that's happening in the lab. And we'll get into some of the details as we go through our conversation. But I think as a scientist, you kind of need a little bit of inspiration and motivation, or perhaps a run on those tough days when you're stuck on something. So do you have a favorite quote or a saying, Leo, or something that just keeps you motivated and inspired?
There's a saying by Michael Faraday, in nature's book of secrecy, a little I can read. So I like this quote so much because it captures both the humility and excitement of scientific discovery. We're constantly trying to learn, but there's always a lot more to discover. So that's perfectly captured by this one quote. And that also describes essentially our everyday life in a lab.
Do you find that you're drawing inspiration from nature as you're sort of building these sandwiches at the atomic level, as you described?
Yes, absolutely. It seemed like we're doing something that seemed very straightforward, but the outcome most of the times or sometimes is completely surprising. So those are the moments that we live for. And we're kind of reading into nature's book of secrecy, and whatever little new things we find are super exciting.
I think that's wonderful. And I think it's wonderful to share the excitement with other people in the lab or your colleagues, peers, mentors. So when you look back over the course of your career, Leo, are there certain people who you've looked up to or perhaps celebrated with or maybe helped you get to where you are today?
Yes, there are many people who play very big roles in my journey as a scientist. I could probably point to this one person, my postdoc advisor, Professor Corey Dean at Columbia University. He pretty much exemplifies what I aspire to be as a scientist, someone who not only makes groundbreaking discoveries, but also mentors the next generation. What's most unique about Corey is his ability to see beyond conventional approaches and come up with outstanding solution that's just very intriguing. He's the one who developed the stacking technique of how to build these sandwiches of the 2D material. And as I was working with him over the years, he showed me sometimes that simplest solution can lead to most profound discoveries. At the same time, I also learned from him that a good work ethic and innovative mindset are important to how you do research. So Corey will be the role model in this case.
Excellent. And I love some of those lessons that you shared. I think it's so important to have these mentors and role models who have been there, done that, and they can impart some of their wisdom so you don't have to learn everything the hard way. But let's talk about your journey next. So, Leo, how did you first get interested in science, or perhaps first get interested in physics specifically?
That's a bit of a long story, but I got into physics quite early on in middle school. It seemed to be a subject that comes with them, right? It's something that I'm interested to just dive into myself outside of school. So that led to me majoring in physics in college. And then I continued in grad school at Northwestern under my advisor, William Halpring, where I studied superfluid helium-3 using a pulsed NMR technique. And after graduating, I kind of pivoted to a new direction. My postdoc with Corey Dean at the Columbia shifted to a different research direction of 2D material. That's what we were discussing earlier. This is where I learned how to fabricate and assemble van der Waals heterostructure. And during my time at Columbia, we kind of pioneered the technique of using precise layer stacking and the interfacial engineering to unlock exotic quantum phenomenon. The work that led to this interview, the fractional exciton, kind of is a continuation of the work I did at Columbia. Now in my lab at Brown, we explore electronic behavior in a wider range of van der Waals structures. And apart from just assembling these 2D sandwiches, we also had a track record of developing new measurement techniques like Coulomb screening measurement or angle result transport measurement. But in general, we study emerging phenomenon of these electrons confined in a two-dimensional environment. And we use different ways of building sandwich to create new flavor profile. So by doing this, we're hoping to push the boundary of low-dimensional quantum physics.
I think this is fascinating. And I'm curious, I think when people are going through the scientific pathway, it's not always clear what the end destination is. How did you know that you wanted to pursue a career in academic research, or did you consider any alternative paths?
No, I did. I think for most physics students or researchers in training, there's always this big doubt, would I be able to do it? I went through that phase when I was a postdoc, and as I was going into transitioning to look for potential positions in academia. And I thought it would be perhaps equally exciting if I were to just get a research position in national labs or in the industry. So that's the alternative route I considered. But I'm glad that I ended up where I am, because apart from research and apart from physics, working with students and working with the new generation of physicists is a very unique experience.
So how did you choose Brown University ultimately to set up your lab?
They're the one who made the offer, and the process of applying to different universities and getting an offer and navigating the negotiation process is something that I was not trained for at all. The fact that I have an offer from Brown, right, have the opportunity to start my own group, it's kind of unbelievable.
I think a lot of people who have gone through it have experienced the same thing you did, where you get to this point where you weren't trained or prepared to sort of negotiate your position, advocate for yourself, even go through the interview process in some cases. And I think it's something where you really have to grow a lot very quickly to be able to secure that academic position.
Yes, exactly.
But it sounds like you found a great fit there at Brown. You are doing remarkable research in your lab, Leo. So is there a project that you're working on right now, or one that you've completed recently that you'd like to tell us more about that you are just so excited about?
So that's kind of an exciting discovery that we have been working on for a little bit. This is the observation of new type of exciton in quantum Hall bilayer. So the reason that this is exciting is for the following reasons. Quantum particles usually fall into two categories. It's either bosons or fermions. Fermions are like the bricks of the universe. It puts everything together, and boson is a glue that holds everything in their place. And a few decades ago, there's a new type of particle that got discovered. It's called anion. They don't behave the same way as boson and fermion. In fact, they don't even carry fundamental charge. They carry actually a fraction of electron charge. And that was a big breakthrough. So excitons has been studied for a long time, and we always see exciton as bosons. And in this work, we took a long and hard look at the existence of excitons that coexist with fraction quantum Hall effect. And what we discovered is that it's entirely possible for exciton to behave as anyons instead of bosons. So that's one exciting thing that we discovered. The second exciting thing is that this type of exciton, we call it fractional exciton, they don't carry any charge. They're charge neutral overall. As a result, this is a unprecedented kind of new particle that could unlock new questions in the research field of quantum physics. And that's something that we're working on. I'm super excited about.
I think this is remarkable. So how did you know, or do you remember that moment where you started to realize this is something new that hadn't been described before?
Yeah, absolutely. I think we were measuring in the National High Magnetic Field Lab in Florida. And as the data is coming out, we see the fractional quantum Hall effect first, and then we see signature of the charge neutral exciton. As it's coming out, I was definitely excited because this is something new. And then at the same time, it presents me with lots of open questions as to what exactly this is. Could there be alternative possibilities? And then we started to talk to Professor Dima Feldman, a theorist, our theoretical collaborator at Brown University. And through lots of discussions, that kind of allow us to discover the story that's reported in the paper.
Well, I think that is absolutely remarkable. One of these true eureka moments in science that I think are so rare that you have to take a moment to enjoy the moment and celebrate it for sure. So how did you celebrate this exciting success?
So every time a student or researcher have a big publication, we usually throw a party and everybody in the lab and also our collaborators come together. I think we had champagne, we have some snacks and cake and just hang out for quite a bit.
So then thinking about the future, what are some of the implications of this finding of this new fractional exciton particle?
I think that once you have a new type of particle, then the question that arises is what will be the low temperature ground state of this new type of particle? As I mentioned, the excitons, we usually see them as bosons. So at low enough temperature, you're supposed to get a boson-Einstein condensation that has been discovered, and the ground state is a superfluid phase. So now that we have a new type of exciton that behaves more like anion instead of boson, then the question is, what will be the ground state? It definitely shouldn't be a boson-Einstein condensation. And there are theoretical discussion in the past of a anionic superconductor. So it'll be very interesting for us to explore this more and see whether or not there is a anionic superconductor. If not, what else? So we have lots of open questions at hand that we're very excited to look into.
Well, Leo, I think this is so cool. And I know, unfortunately, not every day you have a major groundbreaking discovery in the field, though that would be fabulous. So there are these difficult days, these struggles, these failures that scientists have to go through as well. So do you have an example that you could share with us, Leo, of one of these times where you really struggled with something or you had a major failure? And if so, could you talk us through how you got through that tough time?
I think that led me to the third year in grad school. I was running experiment on a apparatus called dilution refrigerator. It's supposed to cool down the sample to ultra low temperature, sub-millicoulomb temperature. And in my third year, that apparatus, the dilution fridge, developed a super leak. It started to leak the mixture into the vacuum environment when the temperature goes below 10 millicoulomb. And that was a big problem because one, with the leak, I won't be able to achieve low enough temperature to do my experiment. And two, because the leak only developed in the ultra low temperature, I won't be able to do leak check at room temperature. So as a third year grad student, I don't really have a lot in my toolbox to address this.
Right.
There's a lot of panic and frustration, but my thesis advisor, Bill Halpern, offered me a lot of guidance through that time. We did a lot of troubleshooting together. We did a lot of procedure that's still kind of mind-blowing when I look back. We essentially have to unsolder the fridge piece by piece and plug it up and do a low temperature leak check. So that's what I learned, right? There are lots of things that's completely out of our control, but there are things that's within our control. As a scientist, we learn to think in a systematic way, and we learn to dissect a problem following a procedure that's most logical. So instead of letting frustration take over, I just focus on what I could control. It took us, I think, close to 6 months to go through all these procedures. I worked very hard every day, and eventually we figured out the issue, and I got to do some really exciting experiments. So that was probably the biggest challenge I encountered. And it's also the incident I learned the most from.
Definitely. This sounds like a nightmare. Do you think this painstaking troubleshooting that you had to go through maybe prepared you for other equipment failures in the future?
Absolutely. I remember my advisor told me one day that this probably seems very frustrating right now, but you're building great characters and this will come in handy in the future. Being able to navigate in that kind of situation is exactly what experimental physics is about.
Definitely. And I think building those skills early on is helpful as opposed to when you're struggling as an assistant professor to get your lab going. So good, I suppose, that you had this experience relatively early, but we don't want to dwell on just the tough times. I think the perseverance is critical to drive you through these difficulties to have success in your research. And we mentioned a very big recent success that you've had. Do you have another success story that you'd like to share with us, even if it's just a small one that happened recently?
One of the most rewarding experience being a physicist is seeing students grow into confident scientists in the lab. So recently I watched several students go through this process. They start from being a junior student, not very certain about lots of things, to independently designing experiments and carrying out projects and mentoring others. Their growth through the challenges, learning from failed procedures, troubleshooting equipment issues, and mastering complex techniques, epitomize what scientific training is about. And what makes this especially meaningful is to know that these students will carry these skills forward, becoming the next generation of scientists who will tackle tomorrow's research challenges. So the progression from MT to mentor is particularly rewarding, seeing former students now guiding new students through the same challenges they once faced. The cycle of learning and teaching is vital to advancing science. It's also the biggest rewarding experience for me. Every time that happens, that's a pretty big success for me.
Definitely. And I really like this idea that you have people in your laboratory who are learning from you, certainly, but also learning from each other. And I think that's also a good skill or sort of habit to develop early on as a scientist. So if you had to maybe describe your mentorship style in terms of how you work with students and how you guide them through this process, how do you describe what kind of mentor you are?
Maybe I can be characterized as being patient. I let them make their decision, make their own mistake, knowing that everything will likely be okay. And also, since we're exploring unknown territory, my idea of what could work might not be the only way for this to work. So I let them explore a little bit. But at the same time, when something very exciting comes up, I do work very closely with the student or researcher in that group. For example, the discovery of the fractional exciton. Once we saw the signature that combines fractional quantum artifact with exciton formation, we worked very fast together and we submitted the paper essentially just a couple months after the discovery. So there's two sides of this.
Well, I think that's great to give students the freedom to really explore their own ideas as well as put the guardrails on when they're needed and help them kind of get to that last mile finish line. Well, we've talked about your laboratory, and I think having these exciting discoveries can motivate you to get in the lab every day and work even harder and harder. But we like to encourage our listeners out there to also take a break sometimes, to read for fun, to broaden their mind, to think about other things. So if our listeners are looking for a new book to add to their reading list, Leo, do you have a recommendation you could share with us, whether it's related to science or not?
Well, a book that I could talk about here is this book that my daughter and I have deeply bonded over. Its name is Pride and Prejudice. It is a very classic book. I've read it many times myself. And as my daughter started to get into it as well, we really enjoyed discussing this book together. We discussed the characters' decisions and motivations. And that discussion also brings out our unique perspective, her insight and my more analytical approach. So I've discovered that this is actually a wonderful way to connect across generations and also to get my daughter a little interested in this analytical way of looking at the world through reading the book Pride and Prejudice together.
I love it. You're sort of sneakily inserting the scientific thinking into the everyday discussions. I think that's wonderful. Well, listeners, we will add Pride and Prejudice to the website. A great book if you haven't had a chance to pick it up and read it. And we've talked about some different aspects of the work that you do, Leo. And I think in terms of the everyday activities of a scientist, there's definitely work in the lab, mentoring students, but you also get to travel quite a bit to work with collaborators, for training, to go to conferences. So when you think about your career, is there one particular place that you've been that was just your absolute favorite? And if so, could you tell us about it?
So you're right that one of the perks of this job is to travel, to go to conferences, give talks, and connect with physicists all over the world. And I've been to quite a few places that left very deep memories. But the one place I guess I want to highlight here is the National High Magnetic Field Lab in Tallahassee, Florida. I've been there many times, mostly to do experiments. And that's also why it's the one place that I want to highlight. A lot of the discovery we make, we need access to really high magnetic field lab. And usually the mag lab in Tallahassee is the one place we can get access to it. So I started going when I was a postdoc. I go there very often. And this recent work we just talked about is also kind of discovered over there. So I love this place so much because we always get to get a peek into nature's secret when we can do experiment in the presence of high magnetic field. So that's the one place I want to highlight.
Oh, very cool. And if our listeners haven't seen pictures or been to this National High Magnetic Field Lab, what does it look like?
It looks like on the outside, a very large facility, a very large building. And it has inside, there are very large magnets that's powered by electricity and very high towers of cooling water. Outside doesn't look much, but I really recommend that you take a look inside where they give tours. They guide you through different cells of different type of magnet and the amount of power they need to power this, and also the all kinds of fascinating discoveries people are making in there on a daily basis.
Oh, that's so cool. And these experiments that you run there, about how long do the experiments run for?
When we usually go to the magnetic field lab, we usually get 1 week of time. So that's the 1 week we really explore the experiment under the high field condition. And in our own lab, we also have access to low temperature and medium magnetic field up to 14 Tesla. And that experiment can run at home. That can run a little longer, usually several months to 1 year, maybe.
And it sounds like you've been down to this lab in Tallahassee, Florida quite a few times. Have you been able to explore and do a little bit of sightseeing as well?
Yes, over the years, I did a little bit of that. And I like that aspect of Florida as well. Usually in New England, in winter, it could get pretty chilly. So when you go visit Florida in winter times, it's a very welcome change in weather.
Definitely. Are there things that you like to do when you're there, when you leave the lab at the end of the day?
Yeah, so when we are in the high mag lab, end of the day usually is very late, usually running past midnight. So when we do leave the lab, we just sleep and come back as soon as we could, because the limited 1 week time, it's essentially 24/7.
You have to make the most of it.
Yes, exactly.
Well, it sounds like this is a fantastic experience. And then do the students get to accompany you as well when you go?
Yes. In fact, now the students go most of the time, and I go whenever I could when teaching allows. So there's another part of activity I have to balance. I can't just enjoy visiting my lab all the time.
That makes sense. Well, it sounds like this is a great experience and perhaps a group bonding experience to sort of pack as much as you can into that 1 week and then return exhausted to the lab to explore all the findings.
Yes, exactly.
Well, I think this is a wonderful thing to be exposing students to as well, giving them the opportunity to get out there and kind of see what it's like, boots on the ground, doing these kinds of experiments. And I think the people that you work with in science are part of what makes it so remarkable. You mentioned how rewarding it is to be able to train this next generation and to work with colleagues and collaborators. And I think the scientists that I know are these warm, wonderful, funny, creative people, and that's not often how they're portrayed in the media, unfortunately. So we try to break some of the stereotypes that people have on our show by just talking about these human moments in science that go contrary to what people might expect. So Leo, do you have an example of whether it's a quirky tradition or just a funny or fond memory that you shared with colleagues that fits the bill?
Yes, we have one of those. When I was a grad student, at the beginning, I had a roommate and we share one cat, a black cat. So later on, my roommate, as a gift to me, he got 2 t-shirts with the cat pictures on the t-shirt. And we took a picture together in the lab wearing this cat t-shirt. And after we graduated several years later, our lab mate turned that picture of us wearing cat t-shirt into their own t-shirt. So it's t-shirt with us wearing the cat t-shirt. And they took picture of wearing this and sent to everyone. Recently, we returned to Northwestern to celebrate our advisor's retirement. That's when my roommate and I recreated the original photo. We each got our partner in a photo with that t-shirt, and then we're wearing the t-shirt with the t-shirt with the t-shirt. And this tradition came full circle at my wedding recently when my wife surprised everybody by gifting these meta photo t-shirt to all my lab mates who were at the wedding.
That's amazing.
And our advisor was so amused, he took 3 of them home. So the original cat photo lives on in many renditions now.
So what was the cat's name?
The cat's name's Dexter.
Dexter's pretty much famous in your laboratory at this point then.
Yes, very much.
I love it. I think this does showcase the sense of humor and sense of fun in science that, you're right, people don't often get to see this, but I think it's pervasive in really every laboratory that I've worked in. So I think that is remarkable. And you are working hard to answer some very difficult questions in science and physics. Oftentimes you face difficulties, whether it's time at the magnetic field lab, whether it's just limited funding, staff, even just the feasibility of these big questions you're trying to tackle. So if we took away, Leo, all the barriers that normally hold you back, is there one particular question or problem that you would want to address first?
I think that this kind of builds on the fractional exciton that we were discussing earlier. If we take away the limitation of funding, staff, technology, or even feasibility, right? I would like to see if I can get excitons, fractional excitons, to behave like a type of particle called non-abelian anion. And on top of that, what that means is that when you take 2 of them and you switch their position, each of them will morph into a new form that's unrelated to its original form. So that's one of the most fascinating ideas in quantum physics that I think about, but we don't really have a way of doing this as of now. So if you remove all the limiters, I'd like to see if I can get non-abelian fractional excitons and observe how they behave when I switch their positions.
Interesting. So what do you see maybe as the biggest limitation? What is preventing you from doing it?
There are 2 layers of this. One is to stabilize this kind of particle that's non-abelian. Another one is to figure out how to exactly switch their position and absorb how they morph, how they change, how they evolve. And on an experimental level, these 2 are both highly challenging.
Well, that makes sense. Well, this is a fascinating problem for us to ponder today. We appreciate you sharing this big dream project with us. And we've talked about a lot of different things today. I'd love to end by chatting about advice. So, Leo, when you think about your career path, is there one piece of advice that somebody gave you at some point that really helped you that you can share with our listeners today?
The advice will be to take on hard challenges, but be patient with yourself through the process, because progress in science, just like in life, isn't linear. What matters is staying curious and resilient and motivated.
Well, I think that's a fantastic message to share with listeners. Is there any other last piece of advice from you personally, or a last note of inspiration that you'd like to leave everybody with at the end of our conversation today?
I guess science needs both creativity and perseverance. And it's important to remember that even failed experiments teach us something valuable. And it's also important to find collaborators and mentors who share your enthusiasm. And the advance of science is a community effort instead of an individual activity.
I love that message. And I think so important today more than ever, where these large collaborative projects are becoming more and more prominent. And it goes against what people often think about this sort of lone scientist working in the lab by themselves. Well, we appreciate you sharing these insights with us today. Leo, if our listeners want to learn more about you and the exciting research that you're doing, how should they get in touch, or what's the best way for them to discover more?
Email is probably the best way to reach me. My email is ja_lee@brown.edu.
Excellent. Well, listeners, definitely get in touch if you have any questions for Leo. Check out the Brown website if you want to find out more about Leo's research. And Leo, it's been a pleasure to chat with you on the show today. Thank you so much for your time.
Thank you very much for having me. It's been fun.
Well, it's been great to hear more about you and your work. Listeners, wonderful to have you here with us as well. We hope you join us again next time for another episode of People Behind the Science.